Now that we know what it means for a matrix to be invertible, let's turn to answering when a matrix might be invertible. So we want an efficient computational tool, so we will phrase this in terms of the matrix rather than the transformation. So assume first that we have an invertible matrix transformation T defined by the matrix A. So our first observation is that for every B in Rm, B must necessarily lie in the span of the matrix A. And this is because of the invertibility. And moreover, the solution to such an equation is necessarily unique. For if there were a second vector, x prime, such that t x prime equals b, then we can apply t inverse to both sides to see that x and x prime must be the same. So this yields two useful pieces of information about our matrix A. The first observation is that the span of our vectors v1 through vm is all of Rm. This tells us that there is necessarily a pivot in every row of A. The second observation, that we can express every element in the image of T as a linear combination of the columns of A uniquely, tells us that the columns of A are linearly independent. So every column of A contains a pivot position. This tells us that it is necessary for our matrix to be row equivalent to the identity matrix. For example, as you may have already guessed, the rotation matrices A, whose first column is cosine theta sine theta, and whose second column is minus sine theta cosine theta, are all invertible matrices. In fact, the inverse corresponds to a rotation by negative theta radians. So we explicitly determine the row equivalence between A and the 2 by 2 identity matrix for theta equals pi over 4 using the following operations. First, we subtract row 1 from row 2. Then we add 1/2 of row 2 to row 1. Then we scale row 1 by root 2 and scale row 2 by root 2. This last example is, of course, instructive. If we recall that it is possible to encode our row operations as matrices, then we've actually shown something better than what we originally anticipated. An M by M matrix A is invertible if and only if the reduced row echelon form of A is the identity matrix. So to see how this works in practice, we're going to use our row operations from the last example to construct the inverse of our matrix. So we're going to call the matrices corresponding to our row operations O, and the subscript corresponds to the order in which we perform these operations. The first one, we're going to call O1, corresponds to R2 minus R1. And that's, of course, encoded by the matrix 1 minus 1, 0, 1. The second operation that we encoded was R1 plus 1/2 R2. This, of course, corresponds to the matrix with entries 1, 0 and 1/2, 1. Our third operation was scaling row 1 by root 2, and our fourth operation was scaling row 2 by root 2 over 2. Now, if we think about this as an encoding by multiplication on the left, then we can think about our original matrix A, which was root 2 over 2 root 2 over 2, minus root 2 over 2, root 2 over 2. Our first row operation can be encoded by multiplying this matrix by O1. Our next row operation is encoded by multiplying the result by O2. Then we can multiply by O3, and finally multiply by O4. The result of this is simply the identity matrix I. So this tells us if we take the 4 operations corresponding to the 4 steps in the Gaussian elimination algorithm and multiply them together from left to right, last operation to first, then we'll get the inverse of our matrix A. So of course we can check our intuition. If you sat down and multiplied O4 times O3 times O2 times O1, we would get the matrix with entries root 2 over 2, minus root 2 over 2, root 2 over 2, root 2 over 2, which of course is the rotation matrix corresponding to rotating pi over 4 radians clockwise, or you can think about this as negative pi over 4 radians. So of course, at the onset of this process, we said that we would like to be able to do this computation efficiently. In this course, efficient really means that we can make Sage do it for us without intervention. Our last example is clearly not efficient. So let's try something different. Let's assume that our matrix A is an invertible m by n matrix, and let's simply observe that A times A inverse is the identity matrix, which has columns E1 down to EM. If we regard the matrix A inverse as an unknown, then we could actually think of this like a system of equations corresponding to the m by 2m augmented matrix A bar I. Now, if we perform Gaussian elimination, then we can think of the solutions not so much as values for particular variables, but as the columns of a matrix. So for example, let us compute the inverse of the matrix A with columns 1, minus 3, 2, 3, minus 6, 0, and minus 2, 3, minus 2. To do this, we simply set up the following augmented matrix. If we enter this 3 by 6 matrix into Sage, and then ask it to row reduce the matrix for us, we will get the following matrix. The right-hand side of this, of course, gives us the columns of our matrix A inverse. And of course, you could check using Sage that if you define the matrix A and you define the matrix A inverse, if you multiply those two matrices together in either order, you will get the 3 by 3 identity matrix. And that's it. That's all you need to know about how to compute the inverse of a matrix.